Hi everyone, in this lecture we will talk more about bitwise operators. So the operators that we discussed were bitwise AND, we have bitwise OR, and we have bitwise NOT. Okay, we have bitwise XOR also. So let's see one by one how these operators are going to work, right? So first of all, let's see how an AND gate works, right? So what does it mean to AND two bits? So let's say if you have bit 1 and you do it AND with bit 1, you will get a 1. If you have 1, you do a AND with 0, you will get a 0. 0 and 1 is also 0, and 0 and 0 is also 0. So these are the basic rules of AND. Similarly, you have the rules of OR. 1 or 1, okay, is 1. 1 or 0 is also 1. 0 or 1 is also 1, and 0 or 0 is also 0. So OR evaluates to 1 if one of the bits is 1, and AND evaluates to 1 if both of the bits are 1. So both of these and the XOR also, they are binary operators, right? So which means they need two operands. So what does it mean if we do an AND of two numbers? For example, if you have a number A which is 5, if you have a number B which is 7, and suppose you do A and B. So what it is going to do, it is going to perform an AND operation on a bit level. So 5 is represented like this. So 5 is stored like this inside the memory, and 7 is stored like this inside the memory. So when you're going to do an AND, you will see this will be 0, and 1 will be 1, 1 and 0 will be 0, and this will be 1. So your output will be 5 in this case, right? And if you do this is 5 and 7, right? So this output will be 5. And if you do 5 and 6, so 5 is 101, 6 is 110, so you will get 1 here, you will get 0 here, you will get a 0 here. So this answer will be nothing but 4, right? Similarly, you can perform OR. So let's do 5 or 6. So 5 is 101, 6 is 110, so this is 1, this is 1, this is also 1, so this will be 7. So this is how bitwise operators are going to work. So let us also think about XOR. So in XOR stands for exclusive OR, which means if you do 1 XOR 1, it is going to be 0. 1 XOR 0 is going to be 1. 0 XOR 1 is going to be 1. 0 XOR 0, it is going to be 0. So exclusive OR means exactly one bit is 1. Okay, out of 2 bits, exactly one of them is 1, only then you are going to get a 1 here. If both the bits are same, then you are going to get 0. So let's do 5 XOR 7. So if I do 5 XOR 7 here, so 5 is 101, 7 is this, and if I do a XOR, so it will be 0, it will be 0, it will be 1. So this answer will be 2. 5 XOR 7 will give me 2. Another property of XOR is XOR of numbers which are same will be 0. For example, if you do 5 XOR 5, it will be 0. You can verify, right? So this will be 0 0 0. So this number turns out to be 0. And if you do 5 XOR 7 XOR 5, then it will give you 7, because the bits of 5 will cancel out. For example, if you do 5, then you XOR it with 7, then you get 0 1 0. You again do XOR with 5, you will get 1 1 1 here, which is nothing but 7, right? So this is same as doing 5 XOR 5 XOR 7, and something, this is 0, right? So 0 XOR something is something, so this is going to be 7. So this is how bitwise XOR works, right? Let's talk about next operator, which is NOT. Okay, so NOT, basically it will flip the bits, right? Flip all bits. So if you have a number like this, If the number is 1, then it will make it 0. If the number is 0, it is going to make it 1. So this is, you can try bitwise not. Then let's also talk about shift operators, right? So we have basically two types of operators. This is called left shift and this is called right shift. So okay, so let's see what does left shift does. So if I say, and these are also binary operators, which means you need two operands to operate on. So if I do 5 left shift 1, okay, that basically means in the binary representation of 5, we are going to shift all bits by one position towards left, one position to left. This would mean you will discard the leftmost bit and you will insert a 0 from here, right? So your originally the number was 5, it was this, now your number is 1010, which means you have multiplied this number by 2. This is 5, this number is 10. And why this is going to happen is, so left shift 1 means multiplication by 2. Okay, so if you're doing a left shift 1, so it is same as doing a equals to a into 2. So if you do this, a equals to a left shift 1, so it means a equals to a into 2. For example, this number is 5 and this number is 10, and the reason why this happens is because this is hidden in the powers of 2. So if you clearly see, this is 2 raised to the power 0 into 1, this is 2 raised to the power 1 into 0, this is 2 raised to the power 2. So you can express 5 as 2 square plus 2 raised to the power 0. Okay, so this is how you express 5. Okay, but this number is nothing but 5. But if you do a left shift here, right, so how do you write this? So this is 2 raised to the power 0, 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3. So this can be written as 2 raised to the power 3 plus 2 raised to the power 1. So you can take out 2 raised to the power 1 common, and this becomes 2 square plus 2 raised to the power 0. So this is nothing but, this is 2 into this number is 5. So you are actually multiplying your original number by 2. So this is what left shift by 1 means. But you can also do left shift by 2. So you can say a equals to a left shift 2. So if your number is, let's say, equals to 5, then a left shift 2 means you will insert 2 zeros from the left, and the extra 2 bits that you have on this side, they will be discarded. Now if you see, this number is 20. Okay, so here you are multiplying 2 times by 2, 2 times by 2. So if your original number is 5, then 5 left shift 2 will be equal to 5 multiplied by 2 into 2. That means 5 multiplied by 2 square. Similarly, if a left shift b would mean a is multiplied by 2 raised to the power b. 2 is multiplied b number of times. So this is why we can say left shift means multiplication by 2. Okay, multiplication by some power of 2. And we also have right shift. So right shift performs the opposite, right? So right shift does division. Okay, if I say, okay, a right shift b, it is equivalent to a divided by 2 raised to the power b. Let's see one example. Now if you have a equals to 10, this number is 1010, and you do, okay, a right shift 1, so it would mean discard the bits, discard one bit from the right and add 10 from the left. So this number now becomes 101, which is 5. So, and maybe you do it again, so you discard this bit, now this number becomes nothing but 2. Maybe you do it once more, a left right shift 1, so you discard this bit, you add a 0 from this side, so this number becomes 1. This is 1, and you do it once again, this number becomes 0 now. So you discard this, you're left with zeros. Okay, so we started with 10, we came to 5, we came to 2, we came to 1, we came to 0. You could have also done, if the number is 1010, you could do, if this is a, okay, a is 10, and binary, this is how it looks like. So if you do a right shift 3, which means you will discard 3 digits from the right and you will add 3 zeros from the left, so this number becomes 1. And this is same as doing right shift 3 times, so your number becomes 1. So you do 10 divided by 2 raised to the power 3, which is 10 divided by 8, and since this is an integer division, the output is 1. So this is what left shift does, and this is what right shift does. Okay, so this is how you can do left shift and right shift, and this is about bitwise operators.